Just to review, we're doing carbohydrates. Remember, the carbohydrates, since it's a sugar and has an alcohol, or has at least one, if not more alcohols on it, it can be both oxidized and reduced. If it becomes oxidized, in this instance here, we're talking that at that position it becomes a lactone, specific ester. Okay, and it's called a reducing sugar. There are times that could be replaced, and we'll talk about that in a moment, by another glycosidic bond where it couldn't be reduced. But that has an end that's available for reducing, and so that's important later on. We'll talk about the reasons why, or give one example, I should say, about the reasons why that is important. If you can do oxidation, you can also do reduction. And in this instance here, we're making what's called an alditol in this one, because it went from an aldose, so becoming an alditol. And this is one example. This one's sorbitol. And with sorbitol, just ignore that. And then I just talked a little bit about sorbitol in general, about the fact that it specifically is a sugar substitute, and it can also be a laxative, by the way. But it's the one that's many times in sugar-free gum, but it can be worked. All right, since you have alcohols, move this down. Alcohols are great nucleophiles, so you can have things added to them, since they can go and attack things. Sure, I know this. This is an example here where we're making an ether linkage. So we're methylating it. But the new bond is called a glycosidic bond. So whenever things are attached to the sugar, it's called a glycosidic bond. Okay. Then just because, for more vocabulary, if it was originally a furanose, it's called the furanoside. If it was originally a pyranose, it's called the pyranoside. Remember, furanoses were 5-membered ring sugars. Pyranoses were 6-membered ring sugars. That is a mouthful. All right. Many times we're talking about a glycosidic bond with the anomeric carbon, but there are other modifications that you can make at the other positions. And for some of them, like in vivo inositol, which is a sugar, which is very important for cell signaling. This isn't it. This is glucose, but no, it's highly phosphorylated. It can be, and so it actually depends on which which oxygen is phosphorylated, that it changes what pathway, the cell signaling pathway that it goes. And so they call them the phosphatidyl inositol phosphates, or the PIPs, PIP. And so this is a little side note, and we can actually talk more about them next semester because for inositol signaling. Okay. Do not memorize these. I would give you this table. However, if I gave you, say, for example, galactose, and then I asked you to transform it into, and like a N-acetyl, actually 2 N-acetyl, galactose or whatever, I would keep blinding myself. I would expect you to be able to put the functional group on, okay? And so these are just some of the possibilities that are out there. And so we have amino groups. They can be, so this is, for example, in glucosamine. And so we could add amino groups to them. We could add N-acetyl groups to them, okay, because it's through an amide linkage. It's not directly through the oxygen. You can acetylate them as well to make sure you know your functional groups. You can have methyl groups. You can have lots of things added onto them. And so you can have them deoxy, okay. You can have them where they've been oxidized to the point to where now they're a carboxylic acid, and so on and so forth. Right. So once again, I would have to give you this table rather than having you just add the correct functional group to the sugar, rather than having you memorize everything. Where did it put? Now, some of the ones that are important in vivo. This is a phosphoric ester. These phosphates are really important with respect to metabolic pathways. So next semester we talk about, this is glucose 6-phosphate. We talk about glucose 6-phosphate. We'll talk about like glucose 1-phosphate. You can talk about the 1,6-bisphosphates and all this kind of stuff. So that's why these are very important. Many times, so in vivo, they're going to usually be catalyzed by an enzyme. And so this would be, what class of enzymes would this? Just to practice your classes of enzymes. What class of enzymes transfers a phosphate from an ATP to something else? And your handy list of enzymes. What's that family name called? It's a specific type of transferase. It's a what? Kinase. Kinases transfer phosphate groups using ATP or GTP. Technically, I think it's any of the NTPs, but those are the two movies. Yeah. By the way, this is hexokinase, which is the first step of glycolysis. Okay. And so that's why technically this is just to show you an example of a glycosidic bond, one that's important in the functional group being added. We have the amino sugars. Amino sugars is just where you substitute nitrogen in, okay, for one of the oxygens. So this is NAG. They abbreviate it whenever we were in lab and stuff. Our lab that would call these NAGs, NAGs for N-acetyl beta-glucosamine. And I guess other labs also do this. This is like a common name. And they call this a NAM, N-acetyluramic acid. And so I think I got a picture of it coming up. Oh, because I can't see it. I think I got a picture of it coming up. But these are important for the integrity of bacteria. And so they call them NAM-NAG repeats. So we'll look at examples of it. Okay, so then you can have amino groups as well on there. Okay. This is where we meet the road, so to speak, on this, where the tires hit the pavement. I'm really feeling like going on a road trip right now. I don't know why. Okay, so far we've been talking about single monosaccharides, but in reality, many times we store them, or we either use them as a disaccharide, or we store them in these really huge polysaccharides, okay? And what happens here is a condensation or a hydrolysis reaction, depending on which direction you're going. So in this instance, we can imagine this oxygen, it's a nucleophile. This carbon, the anomeric carbon, can be attacked. So we have smack into that, bang, something has a break or leave. It could be that alcohol that leaves, and we have a new bond. It's now an acetal bond. And so it's called a condensation reaction because water is given off. We have the hydrogen from one oxygen. We have the OH from the anomeric carbon. And that's why it's called the condensation. The reverse can also happen. If you remember from organic chemistry, the acetal formation is completely reversible, which is good because in vivo we need it. We need to be able to store sugars and also break them down. So this is actually the common sugar maltose. Maltose is a disaccharide. Based off of organic chemistry, you should already be able to name these, but I want you to be able to go back and forth. I would give you almost like a little table that says, okay, this is glucose, galactose, mannose, all those, randose, or whatever. And then I would expect you, based off of their names, be able to put them together in the correct linkage. All right. So remember, to review, how do we know what is the difference between alpha and beta? So if we notice here, it's an alpha glucose that's hooking up to the beta glucose. What makes the one on the left an alpha glucose? It's a good review for Monday's quiz. Possibly. It's trans with respect to the what? So what makes this an alpha? How do we know this one's an alpha and this one's a beta?
It's on the opposite side.
The alcohol's on the opposite side of what? With respect to what?
You're talking about that CH2OH up top?
Right.
What's that called?
Well, technically it's a methoxy group, but I call it scorpion's tail. Okay, so that is not the scientific name for it. But to me, it just reminds me of scorpion's tail. So since it curves, it's always drawn, being curved back over. All right. if the alcohol hanging out the anomeric carbon is on the opposite side, or it's trans to it, I just think of opposite and alpha since they both start with vowels, make sure you know, and there's alpha. If you notice on the other one, they're both on the same side. They're cis with respect to each other, and so therefore, they are going to be beta. That is true for D sugars, and almost all of our stuff is D. It's actually the opposite for L, because remember their names are each other. Okay, so just to review from organic chemistry, this right here, what does that YL indicate? It's a group hanging off of something else, like methyl, ethyl, whatever. So that literally means that the alpha D glucopyrinosyl group means there's an alpha D glucopyrinose hanging off of the D glucopyrinose, the other one, okay? So what's new, or what may be new, because I actually, depending upon how much time I always had left over in organic chemistry too, dictated how much bioorganic chemistry I got to cover. But what they do for the sugars is they put in the parentheses what carbons are involved. So this is called a 1,4 linkage because carbon number 1 is now linked to carbon number 4, okay, of the next carbon. And it's important. This is an alpha linkage. So this is an alpha 1,4 linkage. This one doesn't matter so much, okay? All right, so.
If it were a beta linkage with the curve over the top.
Yeah, we're going to see it. This is the way that sometimes you're probably used to seeing these in biochemistry and biology type of books. You'd see something that looks like, I'm not going to draw all the parts in. Whoops. They draw it kind of like curly cues, but in reality, we're going to look at some of the actual structures in a moment. It's not quite that pretty or quite that obvious necessarily. But that would be a beta. In fact, this would be a beta 1,4 linkage. You can also have, by the way, a 1,6 linkage where these two are connected. You can have a 1,1 linkage. You could have 1,2. I guess in theory, a 1,3, it just has to have another alcohol hanging off of it. So that's why they always put the number in. So let's see here. Here we go. So now we're going to be practicing. I'll give everybody a moment to look at it. And for those who've already had the PowerPoints, do not cheat. Do not have to go. Do not have $200. All right, this is sucrose. Sucrose, of course, comes from sugar canes. Unless you're up north, then you can get it from beets. Sugar beets. I mean, you can get sugar beets here too, so that doesn't make sense. This is a catch crop. All right, and so what it is it's a D-glucose and a D-fructose. I showed you the picture. One way to draw it. This is a better way to draw it. And so now I want you to tell me the linkages because that's not the actual answer, I think. So if we just think about this, give you all a moment to look at it, count your carbons, that kind of stuff. If I bring it to correct class, it's always nice. I should not even have that mess up here. Well. Isn't that special? What? Give me a second. This is what, chapter 7, correct? Yes, carbohydrates. I didn't have it up. Okie dokie. All right, so first off, are we starting here? Because this is the anomeric carbon. Are we starting here with carbon number 1, 2, 3, 4, 5, or 6? It's a 1, so I'm just going to write that in. That's a 1. All right. The carbon to which it is, and I do not know where this. What is it? V or whatever, ignore that. That has absolutely, I don't even know where it came from. I can't get it out. It won't let me select and get it out. It's just there. It's a ghost of V. Okay, but the carbon to which it is attacking, or that it's connected to, is that carbon 1, 2, 3, 4, 5, or 6? 2. You know, a lot of people mistakenly call it carbon 1. They forget this one here. But 1, 2, 3, 4, 5, 6. 6, 6, 6, 6. Okay, you always go with the lowest numbers. If you notice this is technically, what's it called? The line has a line of symmetry there. And so you could have counted it this way or that way, but then you go to the lowest numbers because they are equivalent with respect to each other. So it's 1, 2. Now the question is it alpha or beta? Is it an alpha carbon, or is it an alpha alcohol, or a beta? Is this one that's attached? Is it alpha or beta?
It's alpha.
It is alpha. Oh, there it is. It's called an alpha 1,2 glycosidic bond. So let's do another example. This one's lactose. Okay. It's a galactose glucose. Now give me a moment once again to try to figure out, this is one way of drawing it. This is a better way because it is going to be in your confirmation. So I'll let you count the pieces. That's running legal joke. My grandpa used to have, and I think it's because his dad used to also do it, my grandpa. Back in the old days in the holler. So they would deliver the mail, and you had a mailbox at the end of their drive, and he would send us to go out to get the mail, and he'd tell us we had to count the pieces at the mailbox, and we had to come to the house and count them for him to make sure we didn't lose anything. I'm like 12 years old, whatever. Like we're gonna run off with your bills. So, God bless his soul. That grandfather in particular was one who's a native worker. He was a native, of native stock, let's just say. And so he was always talking about, and he grew up in the Depression, talking about how hard things were. He's like, we were barefoot going to school, uphill both directions. That was a little smart aleck. But then like, Grandpa, how do you go uphill both directions? You have to go downhill. Really stupid and somehow. He's like, we walked 6 miles in the rain and the snow and yeah, it's like Okay, so let's start here. For the galactose, what carbon is it that is in the bond? 1, 2, 3, 4, 5, or 6? 1 carbon. Sorry, there's been Sesame Street in my house with my son. Okay, and what carbon is it joined to?
3.
Oh, we've got a debate.
No, I agree.
I heard about 2, 3, and 4. So, how many people say it's carbon number 2? Anyone? Oh, what happened here?
I feel bad for 2.
You feel bad. How many say it's 3? Okay. How many says it's 4?
That's what I was going to say, but now I recounted.
You counted. So normally you didn't vote. This isn't like the U.S. You have to vote. What number of carbon is it? What?
I'll go 4.
He's gonna go 4. Okay, why?
I don't know, just because it isn't symmetric.
Exactly. Thank you for being John the Baptist in the wilderness. Yes, it is not a symmetrical one. This is carbon 1. 1, 2, 3, 4. It's a 1 point. And so, don't give in to peer pressure. Okay. Now, is it an alpha or is it a beta linkage? It's a beta. And so, because the one carbon that's at number 1 is going up, it's a beta carbon from the anomeric. And it's a beta 1,4 glycosidic bond. Next, we have.
So if you're counting from the right and the bottom one, that's why it's 4 on the top. We should count from the right as well.
Bottom and the top. So I'm going to say bottom and top, these are the same thing.
No, that's not what I mean.
Oh, okay.
The different, if they were monosaccharides, like you would number it 1, 2, 3 from the
This
right.
is still 1, and because it's an anomeric carbon,
You
it's
have to count the
asymmetrical,
anomeric
it's an
carbon every
anomeric
time.
carbon. And one of the reasons why is it's going to get top priority, it's asymmetrical, and 2 is because this carbon gets top priority as the anomeric carbon because it's making 2 oxygen bonds. Did you learn about that in organic chemistry? The more carbon to oxygen bonds, the higher the priority. It's why carboxylic acid N is more important than alcohol. And this one right here is only making 1, so it's the pion of the
So
of
if
the
it had
sugar.
that CH2OH bond there on the right, it would be 3, correct?
CH2OH bond on the right.
Right, where the OH is, where we're starting our numbering for 1, that carbon.
This is this
No.
this is oh you can tell
Sorry,
that
this is on the second.
On the
glucose.
D-glucose.
On the D-glucose.
D-glucose, this one.
And the number 1 carbon, if that had a CH2OH attached to it,
Then
it would
correct.
be 3. We would number it 3.
CH2OH. Then
It would be symmetrical.
CH2OH is perfect symmetrical. Then yes, this would be a 3.
Okay.
Got it.
Okay, yeah, I have to draw it. I'm surprised I was able to do with that drawing down. I have to draw things out. Okay. All right. Oh, we actually, I think we already did I don't remember if we did maltose or not. I think we did, but we can do it again if we did. Maltose are 2 glucoses. Yeah.
So you were saying you have to count, so if you count from the bottom from the right, you'd also have to count from the top, is that why it's 4?
So now we have maltose, 2 glucoses. So this one, actually I think we already did this one, but what carbon number would this one be? 1. And this one right here, it was what? Somebody said it.
Is it 4?
It's 4, because there's an anomeric carbon 1, 2, 3, 4. Okay? Right? And is it an alpha linkage or a beta linkage?
Alpha.
Alrighty, see? It's not bad. So it's an alpha 1, 4 glycosidic bond. So you learn, the next thing I'm going to show you, do not memorize. Okay? I would have to provide it for you. Please don't memorize that. Just like the amino acids have a code, the 1 and 3 letter code and abbreviations and stuff like that. And, nucleotides do too. You just learn A, G, C, T, U, that kind of stuff like that. There's also, there are other ones as well. Sugar, there's a sugar code, okay? Or the carbohydrate code. I have to provide this for you. But sometimes you probably have seen this already, where sometimes they have these like little colorful, almost like little figures all linked together in the bottom. That's because you have to look it up. I have problems telling it was hard, but that way you can say, oh, look, this is N-acetyl galactosamine, and that one's just galactosamine based off of that. But they also have 3 letter codes, or I should say they're not all 3 letter, but they all have abbreviations. It's probably the other one. Okay, so I would have to give this to you, and I'd also have to show you, okay, this is what xylose looks like. Draw it, or if I said there's a xylose alpha 1, 4 linkage to hyaluronic acid, and put the pieces together. Just want to let you know that does exist. Okay. Now we're doing on time. Oh, awesome. So now, I don't remember because we're going pretty fast, but one of the reasons why we store, we can store some sugars and carbohydrates. We are limited in capacity. There's a reason why we use fats for our main energy source, not sugars. I usually ask that as a question or something sometimes, like what's our primary energy source, and people say glucose or whatever, and it's wrong. The one exception is what organ in your body does, or there is one organ in your body that does utilize like 120 grams of sugar a day if you're an average, normal, healthy human being. No. Brain. Thank you. And then there's also another cell of some of our bodies that utilizes fructose. Do you know? Only about, I don't know, roughly half of us in here utilize it. That's the sperm. Okay, I don't know. That's one of those little factors that just stuck with me. But yeah, the sperm can utilize fructose. All right. So I mean, you can use fructose as an energy source, but we go to different. All right. So, but we can store it, and there are also structural sugars like chitin and things like that as well. So this is just one showing you that you can categorize this as being homopolysaccharide versus heteropolysaccharide. Homo means it's all the same sugar over and over and over and over again, like glycogen. Or hetero can be like the NAM repeat. Okay, you can also have it unbranched and branched. So that's why it's possible in the same sugar to have multiple branching derivations or denotations. I'm making that word up possibly, but I like it. You can have it marked as being doubly branched. Or not, but you can have branching. Okay. We'll talk a little bit about branching. We talk more about branching and everything like that in next semester. So here's some examples. Cellulose, of course, is what makes paint strong, and it is these really, 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 really long repeating units of beta-1,4 glycoside bonds. Okay. So we can see it. They like to write it this way. So that's why the little cartoony way is this little curly Q. I don't know why I'm not doing something. A little curly Q thing. And the way that no, don't do that. God only knows I'd probably hook up, accidentally go into some weird network, since I keep drawing a following with people with Arabic names. Okay, so we're not going to join the network there, okay. But, so we have this beta-1,4 unit, but if you thought about it, you'd say that's not very strong, just have these really long, unbranched fibers. But alcohol, they're so alcohol heavy that they can hydrogen bond in between. And so not only do you have these long fibers, but then they hydrogen bond. So there's a lot of intramolecular bonding that's occurring. All right. Some other examples. This is starch. Okay. So I just always go talk a little bit about amylose versus amylopectin. Amylose is unbranched, amylopectin is highly branched. But these can be huge. Like this one, if you notice, there's 4,000 of them in a row. We're not talking like 10. Okay, so 4,000 of them in a row. And the only difference between them is the fact that this one, amylopectin, has a branching at positions 1 and 6 every so often. Every 24 to 30 units, it branches again. We have amylases. So, what are amylases? Enzymes, yes, and they catalyze the hydrolysis. So they help break down that 1,4-glycoside bond. Okay. Does anyone know what? So wait, I'm going to try to draw this. Don't hate me for my ability to draw so well. But we have. I'm going to just draw it as a little cartoony looking thing. Okay. Oh, whoops, I already made a mistake. I was going to make nucleic acid. Oh well, you can't get the idea here. There's an oxygen there that I skipped. Okay, so what we're saying is that amylases can come and break this bond. Amylases cannot break. They are specific to the position on the sugar. They cannot break a 1,6. So does anyone know what enzyme? Sometimes you'll know amylase. What enzyme breaks down that 1,6 branch? What do you suppose is going to remove a branch? No. It's one of my favorite named enzymes. So, because if you're going to remove a branch, you're going to debranch it. It's called the debranching enzyme. Just like you'll forget this for next semester, the enzyme that puts the branch in is called the branching enzyme. Yeah. They do have, like, the enzyme commission does give this really, really long name, but everyone calls it the branching and debranching enzymes. I just like that. This thing is really cool. So here are some of the pictures. Whoa, I didn't mean to do that. Here are some of the pictures to show you the difference between amylose and amylopectin. So you can look at these on your own. This is chitin. So now chitin is a little different in the sense that we see the same kind of things that we've been looking at, except now we actually have another glycosidic bond, and it actually has an N-acetyl group on it that's repeating. Okay? So chitin. Then we have the bacterial cell walls. This is the NAMNAGs that I was talking about. So what kind of, I hit it, what kind of linkage is this? What carbons are linked? Carbon number 1 to carbon number 4. Yes, it is. But see, this means it's repeating, so there's an oxygen there that's repeating carbon. So it's carbon number 4. Okay, so it's a 1-4 linkage. Is it alpha or beta? Oh, we got disagreement. Beta. It's a beta. Okay, because this means it was going up and it has an exponent. So yeah, it's a beta. It's a beta 1-4 linkage. This is the NAM, the N-acetyluronic acid. That's NAG, N-acetylglycosidine. There are ways to try to. This gets incorporated into the cell wall of bacteria. So there are antibiotics that are used to try to block this incorporation. Okay, there's some of these specialty sugars. Because if you block that, then you can, kill off the bacteria. And so this is what whoops, this is the right answer. All right, so this gets even further complicated. So cell wall, we have those NAMNAGs that keeps repeating, but then hanging off of that is, since it has a carboxylic acid or an acyl group right here, you can easily add an amine to make an amide. Which it just so happens, why don't we add a small peptide? Well, not we, the bacteria adds a small peptide. And so if you notice, it's the same 4 amino acids over and over again. Alanine, glutamine, lysine, and alanine once again. Well, lysine has 5, it goes 5 out, and it has another amine. Well, amines can be added to, right? So what it does is we have 4, and then, not we, once again, I say we, it's bacteria, it's not bacteria. But the bacterium would have 4. Then it adds 5 glycines in a row, just as a regular peptide, 5 in a row, which ends with another nitrogen. Okay, that nitrogen then can link to the next big thing over. All right, so this just shows you the thing. So it makes it super, super strong. You can think we have this great lattice work between the sugars and these really small peptides. This is called a tetrapeptide. This one's the pentapeptide. And so this leads over here to the tetrapeptide. Okay. And so it just goes from one to another to another to another. So this is kind of what it looks like. If you look at it, so we have, I can't tell the colors apart. NAG, so NAG, NAM, NAG, NAM. Hanging off of NAM, you've got the 4 tetras. You have it hanging down here. It goes over, ends with the nitrogen. This happens when the nitrogen's going to be hanging on that one. No more, it goes down, it goes over. And so it makes it very, very tough. Okay. And so that's why you can then try to, we can then try to, if there are ways to block its ability to do this. And so we don't do this, but they do this. If we can find a way to block this, then you could potentially break down the cell wall. And so, which, would be a good thing. All right. Oh, I thought I had another one in here. I was taking it out. No, there. I just replaced it. Yeah.
Are do antibiotics work by some of them work by absorbing that
Yes.
Okay.
Mm-hmm. So here's another example. This is one that my lab actually. I didn't work on this project, but another group in my lab did. So these are lipopolysaccharides, which cause endotoxin, which causes toxic shock. And if you notice, you just have a couple of the little sugars that have the lipid hanging off. This is called lipid A, which sticks into that sticks into the membrane, the wall. Then we have a whole bunch of these sugars. These are all sugars. Then you've got the antigen that gets expressed on top of that. Okay? So if you notice, there's this one thing called KDO. KDO is I forgot what KDO actually stands for now. But KDO sugar is the only linkage between the actual bacterium and all this antigen, which causes the bad thing. So one of the enzymes involved here is called LPXC, and it's what adds on that KDO. So one of the projects in my old lab, they determine the mechanism of that enzyme, and they come up with site-specific inhibitors based off the enzyme, just like what you would do, like a competitive inhibitor. What we would do in this last chapter to fight for it, to fight where it can no longer add this on, and therefore makes an antibiotic. Because this was needed in order for the bacterium to live, and it's also the bad part that would cause the phenotype that we would see. Okay. All right. Oh, this is just some more examples. We have heparin, which is a glycosaminoglycan, hyaluronic acid, chondroitin sulfate, which you can actually take as a supplement for your joints, keratin, all these. Once again, they can have a wide range of biological activities. This is what they look like. This is heparin down below, hyaluronic up there at the top. Of course, these are repeated units. Once again, I could, in theory, cover something up and ask you what kind of linkage it is. I could give you little bits and pieces and tell you to draw it out and stuff. But don't sit and memorize all of these. Okay, glycoproteins. You can also add sugars to proteins. Well, we already saw that where peptides were added, but now we can actually have a protein and start adding sugars to it. And this is one of the ways that they can be post-translationally modified. Okay. And in particular, I always like to end with this example of the ABO. It took me forever. This is the old book. This is the way the old book showed ABO. And I'm like, what is going on here? It doesn't, I could not, it took me forever to read this. So, what it is for the A and the B, this is their way of showing an alpha 1-2 linkage, alpha 1-2. Yeah. But the whole idea here is these are almost identical between type A, type B, type A, type B antigen. And if you look, the only difference has to be on the actual non-reducing end. Remember, there's a reducing end and a non-reducing end. This one has an alpha galactose, this has an N-acetylgalactosamine. Okay, and in O, this sugar is just missing. Okay, and so one of the ways that, I hope I put it on there, is this is using the little colored ones to kind of show you what that means. O, it's just missing it. A's got the galactosamine, and the other one's got the galactose, whatever. And so there's, galactosamine, acetylgalactosamine. It's the only difference.
So if they're,
Life and death.
so if they're AB, they both still have their,
Well, because AB means you got one gene from a mother, one gene from your father, and they're both expressed on it. So, okay, just like you can be AO or BO, which is that you have type A or type B. In order to have O, you have to be OO. Okay. How are we doing on time? We have just like a minute left. You can read a little bit more about the whole idea, the craze behind the low carb diets, and why that works, why that doesn't work. You can go into a lot more details with it on next semester. Actually, we go into a lot more detail with the next semester. But the idea is that you keep your carb levels low enough so that way you don't produce insulin. And so, but next semester we actually go over the metabolic pathways involved.